Hey guys, how's it going? And welcome to the video. In this session, I want to discuss the idea of mutable and immutable objects, and more specifically, what I call the illusion of mutability. Basically, what it is, this is something I've seen, especially in beginner programmers. It's kind of the idea that immutable types in Python can look like they are mutable, when obviously that's not the case, even though the appearance is there. So let me show you an example. Suppose I define a is equal to 1, and then do a plus equals 10, and then do a is equal to, let's just do a plus, so just a few ways of changing the same variable here. And then if I go along and then do print a, and we'll do it a few more times down here, and hit run. Okay, 11189. Yeah, cool, oh, nice. So this looks like, I think especially to like the untrained eye, or if you're new in Python, this might look like that a is mutable, right? So it looks like that a starts its life off at 1. We're then adding 10 to it, and we see that result here. We then add 78 to it, and we see it here. So that means it's mutable, right? Well, actually, no, it's incorrect. What's happening here is we're actually redefining what a is. Like if you take out this operator here, all this is really saying is a is equal to a plus 10 here. And if you evaluate this, when this is evaluated, we evaluate it from the right. So this is kind of evaluated first. So if you look at, so a exists as 1. So this is now saying 1 plus 10. So take that 11 and now basically give that 11 to a. But because a already existed, it's basically getting redefined here. So this is getting redefined here, and then same again here. So it's not changing, it's being completely redefined. So basically the old value of a is gone, it's no longer here. However, that identifier of a is now being reused to store the value of 11 and then 89. So what I want to show you today is a foolproof way to figure out if an item is mutable or not. To show this further on, what I'm also going to do is use an actual mutable type, such as a list here. So if I do 10, 20, 30, and then I'm then going to say go into LST of index 1, and this is now equal to hello, like this. And then what we probably want to then do is print off LST. We'll do it before and after the change here. So let's see what we get. Okay, there we go. So that was our kind of before and after there of our list. Now the way we're going to do this is we're going to use a little function called ID. If I open this up here, so it says returns the identity of an object here. In effect, this is you can almost think of this as like asking for the object's memory address. So of course, whenever we have a Python program that's running, the data we're using has to be stored in memory, and those items then looked up in memory, we can then use them in Python, so on and so forth. And of course, memory addresses are unique. So if I do ID of, say, I don't know, let's run it up here, for example. If I do a, followed by the ID of a, we'll quickly blank off the other guys and see what we get. So we get this 4307 here, 53. Of course, this will be different every time, depending on what else is happening on your computer. Python's going to be allocated different spaces to store all of its content in. And now this is where we can prove that this is immutable and it's being redefined. So what we do is replace this, this, and this here. So, right, if an object's mutable, it's obviously going to have a memory address, and then its memory address will then stay the same, but the piece of data in that address will be changed. However, if we run this, check that out, the addresses are different every time. That means that A is not pointing to the same object. It means that A is pointing to a different place in memory. So this kind of, hits home this idea that we're not actually changing the object, we're redefining it. A points to different places of memory here, here, and here, and those correspond to these three IDs, or addresses in quotes, so to speak here. And then to further prove this, what I want to do is do LST and then ID of LST here. So what we should see in this one is we should see the memory address be the same here as it is down here. So if we clear this up, check that out, ends in 21952, 21952 here. So even though we change the contents of the list here, the list is still, it's still pointing of this and this, they still point to the same object in memory. They're still pointing to the same entity, but the entity itself has changed. So that is a truly mutable object. Whereas this here, each time we changed A, we're actually creating like a brand new object in memory. It just so happens to have the same identifier. So we're kind of like, we're swapping out the identifier to say, okay, A points to, this block of memory. Okay, now later on it points to this block, and later on it points to this block. That's all it is. A is just like a pointer to places in memory. There we go. So fairly short one today, but again, it's something that I see come up, especially with beginners a lot. Of course, if you're intermediate and onwards, this is you probably get this already. But my kind of key takeaway for this is, if you're unsure if something's mutable or not, run it through the ID function and have a go at changing it, and then run the ID function again after you've changed it. The key takeaway, if those numbers are different, that means your object is immutable. You're simply redefining what your identifier is pointing to. If your number stays the same, such as with a list, that means that your actual items, its contents are changing, but that is still pointing to the same entity in memory. Cheers for watching, guys. I hope you all have a great week, and see you soon.